Students, good evening, everyone. Am I audible? Students, can you hear me? Okay, good. Okay, so this session is recorded. So this should be available to you later for your access. Okay, first let me complete a small topic which I need to cover in wireless LAN. Of course, this is not tested for your quiz, but will be tested for your final examination. Okay, in the last lecture, we were looking at wireless LAN, and we also looked at what is called the MECA, that is collision avoidance algorithm. I think that part should be clear. So a small topic was left out, that is nothing but distributed systems. Okay? As I explained in the beginning of the discussion of the wireless LAN topic, there are two possible wireless systems. One is the ad hoc, the other one is infrastructure based. Okay? When we say infrastructure based, that means the nodes or hosts cannot directly communicate with each other. They don't communicate. Instead, they communicate with what is called the access points. So this is something like this. So you can see that there is an access point. So just imagine the home network where you have an access point where multiple computers or multiple nodes are connected to the access points. Okay. So this, we call it as infrastructure-based wireless network. So when A wants to communicate to C, so A has to send it to access point, and which access point which then can send it to C. So this is how the communication takes place. So this is similar to the cellular mobile network, where access point is nothing but the cellular mobile tower, and all our mobile devices are the nodes which are mobile. Okay, and you can see that these access points can be connected at the back end by a backend network, let's say Ethernet switches, or let's say routers. So for example, in big organization, okay, one access point can cover only certain region. Okay, let's say this region, and all the nodes A, B, C, they are attached to AP1. Similarly, there is another access point, AP2, okay, which can connect, right, B and D, H. Similarly, AP3. Okay? Suppose A, let's say, wants to communicate to E, they cannot directly communicate. Even they cannot directly communicate through one access point. So what can be done is A sends the frame to AP1, access point 1, and access point 1 will forward it to access point 3 at the back end, and access point 3 will pass the frame to E. Okay, this is how multiple access points are connected by a backend distributed system. Okay. Now the question is this: okay, how these nodes are attached or associated with the access points. So you can see here, A should be associated or attached to AP1. Okay? A cannot be attached to AP2 because it's very far. Okay? Similarly, if you take B is close to both AP1 and AP2. Okay? So at any instant of time, a given node is attached or associated with any one of the access points. If the node is mobile, the access points to which it is attached can change. For example, C may be attached to AP1 at some point. If C starts moving, let's say towards this direction, when it enters into the region or cell of AP2, this may be attached or associated with AP2. So this association can change. So how? So we need a simple protocol by which the nodes are associating themselves with the access points. So that is done by what is called scanning. Okay? So basically, by scanning, the nodes select their access points to which they will be associated with. Okay? And the scanning also should take care of the situation when the nodes move from one cell, that means one region. So this one circle is one cell, okay, to another cell. Okay. Now the process of selecting the access point, we call it as scanning. So what is done is this: the node or the host or our mobile device or laptop or whatever it is, these nodes send a probe frame. Sends a probe frame, okay, periodically. Okay, so probe means it's trying to probe the neighboring access points. All access points within reach will reply with a probe response. So you can see your device. Okay, you can see your device. Okay, when you open it, it can recognize many access points close by. So all the access points within the reach will respond with probe response, and the node will select one access point among others. If it receives probe response from only one, should be fine. It will select one. If it receives from multiple access points, it will choose one among themselves, among the two or three. Then it sends association request frame. So these frames are special control frames. Okay? So very simple. Then the access point replies with association response. So the node sends periodically transmits probe frames, and the access points will reply with a response. They call it as probe response. Hi, I am access point 1. Hi, I am access point 2. This is my specification or data rate, etc. Okay, and the node will select, and it will send another control frame called association request, in which to which the access point will respond with association response. So this will be sent, okay, whenever it joins the network. So it need not be periodic. So I mentioned it should be periodic, it need not be periodic. Whenever a node joins the network, that means, let's say it switched off, or only now it comes close to the network, switched on, only now it is powered on, etc. And whenever it becomes unhappy with the current service, current AP. Okay? For example, let's say C might be receiving service from AP1. Let's say it is associated with AP1. If C is mobile, when it moves away from AP1, at some point of time, when it moves further away, let's say at this point, okay, the service would be poor, may not be happy with the service. So at that time, it will start sending a new probe frame, and it at some point it might receive from both AP1 and AP2. For example, you take B, it might receive AP1, the response from AP1 and AP2, it will choose one of them based on maybe higher data rate or signal strength, etc. Is it okay? And this type of scanning, we call it as active scanning, because the node or host actively involved in initiating the joining process. So active scanning with respect to the node. Alternatively, the access points, they periodically send beacon frames, which basically advertise the access point's capabilities. Okay? So in this case, each access point will send periodically frame called beacon frames, Okay, so that will tell the specification or the capabilities. For example, what is the data rate or transmission rate? Okay. And this beacon frame will be received by the host, individual host. And these hosts or nodes can decide to whom they want to associate. Let's say C decides at some point he wants to associate to AP2, then it will send association request to AP2. Okay. And this type of scanning is called passive scanning. It's passive because it is not initiated by the node, it is initiated by the access points. Okay. And note that when its association changes, let's say C's association changes from AP1 to AP2, okay, so that change will be notified by AP1 to AP2, because at any instant of time, only one should be responsible, either AP1 or AP2. Okay, so when AP2 accepts C as a new member for its region or cell, so that will be properly notified to AP1. So these two will be notified. And the same scanning methods we illustrate, okay, with other illustration, which I take from the other book. So you can see this example, okay, illustration, passive scanning. So you can see that there is AP1 and the circle shows the reachability of AP1. That means this access point can serve any host within the circle. AP2 can serve any nodes in the second circle. And in the case of passive scanning, the first step, number one, is beacon frames are sent from access point. So access point 1 sent a beacon frame, access point 2 sends beacon frame. So these beacon frames are sent periodically. In step number 2, the host, upon receiving two beacon frames, it chooses one. So let's say host 1 chooses AP2. So in that case, in step number 2, it will respond to AP2 by sending an association request frame. Note that it's also a frame, but some bits in the header will tell that it is an association request. It's a control frame. Okay? It's not the normal data frame. Now in step number 3, the AP2, that is the access point 2, will respond with association response message. Now it is done. In the case of active scanning, what the host has to do is in step number 1, it has to send probe request frame. So probe request frame in step number 1 sent by host 1 is received by AP1, then AP2. In step number 2, AP1 and AP2 will respond, number 2, with probe response. In step number 3, host 1 will choose. Here, this example, it chooses AP2, then it sends the association request, number 3. And number 4, AP2 will respond with the response, association response, to confirm the association, that is the end. Now, let's look at the frame format of 802.11. Okay, so this frame format is slightly different from the Ethernet frame format, etc. Right. So at the end, you have CRC for error reduction, 32-bit CRC. And you can see that so there's a request from students go through certain questions in the past year papers. Okay, please wait for a few minutes. There are a few more slides. So the 3 more slides are there. Once I'm done, I'll go through the sample quiz questions. Okay, then we will have time to discuss any doubts and other things. So please don't worry. Okay. So the first 16 bits, which we call it as frame control. Okay, and this is expanded here. The 16 bits are shown here, 2 bits, 2 bits, 4 bits. Next 16 bits duration. That is, when RTS and CTS frames are exchanged, RTS will tell how long the node is requesting to transmit in microseconds. Similarly, CTS will also echo it. Yes, you can send it. So that 16 bits, the duration is represented here. Okay. And these are all the 6-byte or 48-bit addresses. There are 4 addresses, which I will explain slightly later. And the 4th address is not used in the infrastructure mode of Wi-Fi. 4th address is used in ad hoc network. Okay, so we are what we usually use in house or organization is infrastructure-based Wi-Fi. So for that, address 1, 2, 3 will be used. Okay, and we have sequence control. 16-bit sequence control. This represents the sequence number of the frame. Why sequence number is required? So if you look at MECA, the W, the protocol, where at the end of transmission, sorry, when the receiving node receives the frame, it will send an acknowledgement. So that acknowledgement, should specify which frame is acknowledged. So for that purpose, we use this 16-bit sequence number, and it carries payload, and this payload, you can see this represents the bits, how many bits are there. It's basically 2312 bytes. So it uses 2312 bytes. I don't know exactly why this number is chosen, but this is the standard. Okay. And if you look at the first 16 bits, it's called frame control. So it specifies control. The first 2 bits protocol version, and the next six bits, 2 and 4, 2 bits represent type, 4 bits represent subtype. Basically, they tell whether it's a data frame or control frame, or within that, whether it is RTS frame, CTS frame, or acknowledgement frame, or is it a probe frame, probe request, probe response, or association request, association response. Just how we have seen the scanning method, right? So all these, so these bit combinations will tell what type of frame it is. Okay? And these bits to access point, from access point, it specifies the direction, whether the frame is sent to the access point or it is receiving from the access point. Okay? Power management, why Ethernet, there is no power management, sleep and other things. Similarly, Web WEP, this is for encryption, and some bits are reserved. And in terms of the address, as I said, there are 4 addresses. Address 4 is used in ad hoc mode. Address 1 is the destination address. Okay, so the destination address means it's a MAC address of wireless host or AP. If the destination is the host, that represents the MAC address of host. If the destination is, let's say, it's sent towards the access point, that will be the access point's MAC address. Similarly, this is the sender. Address 2 is the MAC address of the sender. It could be wireless host or it could be the access point. Address 3 is the router interface to which the access point is attached. Maybe I can better illustrate with this figure. So you can see that there are hosts, multiple hosts attached to the access point, and the access point is connected to the router. These two router can be integrated into one device, or it could be a separate device, and which is connected to the internet. Now let's see how the frames are sent. So when host 1 sends a frame to the access point, it is basically a Wi-Fi frame. It's not an Ethernet frame, it's a Wi-Fi frame. So in the case of Wi-Fi frame, now the destination is the access point MAC address. The sender is the H1, host MAC address, and the third address will be router 1 interface. So there is an interface here which has a MAC address that also participates in ARP, address resolution protocol, etc. Okay. Now, interestingly, note that when the access point transmits the frame to the router, here it should be a Ethernet frame. The connectivity is Ethernet. So Ethernet has only 2 address fields. destination and the source. So the destination address is R1 router interface MAC address, and the source or the sender here is H1, this MAC address. So this is something like H1, as if H1 is directly connected to the router. H1 is directly connected to the router, and this MAC address is returned. So this is the sender. Similarly, so this is in this direction, host 1 send some frame to internet. Now, if you look at the other direction, let's say from internet, the frame is sent to host 1. So in this case, the router R1, when it sends a frame to the access point, this is going to be an Ethernet frame. So for this frame, Ethernet frame, there are two addresses, the destination address and the source address. Destination address would be the MAC address of host 1. Okay, that's what is available in the router ARP cache. And the sender or source address is R1 MAC address. When it is received by the access point, it will send another frame, the wireless network. That should be a Wi-Fi frame. Wi-Fi frame has three addresses, address 1, address 2, address 3. Address 1 is the destination address. Destination address is H1. Address 2 is the sender, let's say immediate sender, that is this access point. Address 3 is basically the router 1 MAC address. So this is how addresses are used in Wi-Fi, okay, and in the Ethernet when they are connected together to send frame and receive frame to and from the internet. So this is the end of the lecture notes on Wi-Fi, okay. Again, for the test on Wednesday, lecture note 6 topics is not tested. Okay, topics 1, 2, 3, 4, 5. Okay, it's going to be on LT 11. Okay. Any doubt, students? Any doubt on this topic which we discussed today? If there are no doubts, okay, now so let's look at the sample quiz question. So let me share the sample quiz questions. Students, can you see the sample quiz question which I posted?
Yes.
Okay, I'll go through all questions. I think some students are asking specific questions, but I'll go through all questions at the end. Okay, it's a time for a discussion. Of course, if you want to stop me for quick clarification, that is fine. Okay. Question number 1. Okay, note that it's also MCQ based, and usually there is an answer table which I give in page number 2. So this time also it would be something like this. Let me see, just a minute. Okay. And read the instruction carefully, answer all questions. Each question enter the most appropriate choice. This is important. That means sometimes more than one may look correct, okay, but which one you think is most appropriate? That's the one which I want, okay. And only the entries in answer table will be considered. See, for example, okay, here in this case, I put a tick mark here, but in the test, I won't look at the tick mark which you put in the question. What you entered finally in the table, like D, C, C, A, I'm going to look at only the answers. I'm not going to look at your working. Okay, that's important to note. So you need to be careful when you write into the table. Question number 1, what is the minimum bandwidth? Okay, sorry, it's a closed book test. It's a strictly closed book test. So no help sheet, no lecture notes, nothing for reference. What is the minimum bandwidth required if 10,000 byte frames are transmitted in 1 second? That's question number 1. So it's a very simple, straightforward question. 10,000 byte frame, 1000 byte frame means 8,000 bits. So you have to tell in bits, 8,000 bits. 8,000 bits, because it is 10, so you multiply it by 10. So it is 80,000 bits. 80,000, that is 80 kbps. This is the data rate which we want. Now, question number 2, if a packet is 10 microsecond wide on a 10 Mbps link, what is the packet size in bits? So packet size can be specified in time as well as the bits. Okay, so the relationship between these two is the same. The time is something like a transmission time. Okay, is size divided by bandwidth. Time is size divided by bandwidth. So what is the size? Size is time multiplied by, this is time multiplied by bandwidth. Time is 10 microsecond, bandwidth is 10 Mbps. Micro and M will get cancelled when you multiply, so it is 100 bits. Question number 3, assume that host A is transferring a large number of frames to host B using sliding window protocol with window size 10. W is 10. Through 100 kilometer long link, 10 Mbps link. Propagation delay is 5 microsecond per kilometer. That means for the bit, it takes 5 microsecond to travel 1 kilometer. Assume that each frame carries 125 bytes of data. The communication is free of errors, and every frame is individually acknowledged. That means you can straight away use the formula or expression. The question is, how many frames are sent or transferred per second approximately? So this type of questions, okay, already there in the tutorial. So it's a similar question. Okay. So what we should do, because it's a sliding window, first step is you need to find A. Then you need to find 1 plus 2A. Okay. Then you need to compare with W, whether W is less than 1 plus 2A or W is greater than or equal to 1 plus 2A. This is what we are going to do. Okay, it's quite straightforward. So how do you find A? A is nothing but TP by TF. TP by propagation time by transmission time. So, I mean, to save time, I already worked out here. TF is 100 microsecond. How you got 100 microsecond? Transmission time is size divided by bandwidth. Size is 125 bytes. 125 bytes is 1000 bits. 125 multiplied by 8, this is 1000 bits. Size divided by data rate or bandwidth. Data rate is 10 Mbps. So 1000 divided by 10, that is 100 microsecond. What is the propagation time? 5 microsecond per kilometer. The total length is 100 kilometer. So 500 microsecond. That is the propagation time. What is small a? TP by TF, that is number 5. 500 divided by 100, that is 5. What is 1 plus 2a? 11. What is W? W is 10. So W is less than 1 plus 2a. So number of frames transmitted or transferred per second is W frames are sent for every TF plus 2 TP. So when you use the formula, W is known, TF is known, TP is known, you get 9090.91. So that is approximately 9090. Any doubt? So there's a question in the chat. If W is greater than 1 plus 2A, sorry. So if W is greater than 1 plus 2A, as I said, very simple. You just draw the timeline diagram. If W is greater than 1 plus 2A, the utilization is 1. Right? So this is TF. Can you tell me how many frames are sent per unit time? How many frames are sent per second? Can anyone tell the answer? If W is greater than 1 plus 2A or equal to, okay, greater than or equal to 1 plus 2A, the frames are sent continuously. The window will never become empty. So TF, there is no gap. How many frames are sent in 1 second? Very good. So there are few correct answers. Okay, few students responded. Very good. This will be 1 by TF. That's all. Okay, because for every TF, 1 frame is sent. So how many frames are sent in 1 second? 1 by TF. That's all. Okay, good. For the correct answers. So you need to be very careful when you calculate small a, you need to be careful, right? If anything goes wrong, then 1 plus 2a may be wrong. You may end up with wrong answers. Question number 4, IP addresses are more attractive than Ethernet hardware addresses for the purpose of routing. Why? Because A, IP addresses are hierarchical, whereas Ethernet addresses are not. B, IP addresses are just 4 byte long, but Ethernet addresses are longer, which is 6 byte long. C, IP addresses aid or facilitates software-based routing, whereas Ethernet addresses aid hardware-based routing. IP routers are less expensive than Ethernet switches. The answer is the first one, because if you look at the second one, we don't prefer IP addresses for routing just because it is 4 byte long. It's not based on the length of the addresses. Okay, it is based on the hierarchy. IP addresses, some bits will represent the subnet, which you'll be studying in detail in part 2. Okay, that will tell, okay, this is a network in NUS, this is a network in this country. So that is very much required, okay, to forward the frame towards that particular network. So for routing purpose, we want the hierarchy. This is the street number, this is the block number, this is in the floor level, this is the unit number. I want all the hierarchy details. So those details are available in IP addresses, but Ethernet addresses are not. We cannot look into some bits. We can and decide, okay, this host is in Singapore, this host is in China. No, we cannot tell. But network IP address, yes, we can tell where it is. Question number 5. Okay, it's a fun question, but still very few students got it wrong when I asked such questions. You need to be careful. It's very easy to score. The acronym CS stands for computer science. That is correct. Circuit switching, that's also correct. Carrier sense, that's also correct. Collision sense may be correct. But you are supposed to choose the most appropriate in the sense in this context. of our module, the correct answer is carrier sense. So if you look at Ethernet CSMA, we talk about CSMA. So CS stands for carrier sense, not for computer science. Okay. Question number 6. What is the bit sequence transmitted for the message 11101? This, okay, the message is 11101. And we use the CRC, a division polynomial x square plus 1. So the question is, what is the CRC bit? Or what is the bit sequence transmitted, including the CRC bits? Because the CRC polynomial, division polynomial is x square plus 1, it has 3 bits, 101, right? X square 1, there's no x, so 101. So divisor has 3 bits, the remainder will have 2 bits. So the 2 bits can be 00, 01, 10, 11. So whether you get, when you work out, you may, whatever answer you get, that answer will be here. Okay, because all possible 4 answers are here. Now, you need to carry out the division. So again, lecture notes, we have carried out division for one problem. I think we did one more in the tutorial. Anyway, we'll do it here also. So 3 bits. So take first 3 bits, 111. So note that the prefix should be 1. The first bit should be 1. Only then you can divide. Quotient 1, 101. So 1 minus 1, 0, 1, 0, 1 minus 0, 1. So 1, 0. So next 0, you bring it down. It becomes 1, 0, 0. So then 1, quotient 101. So now you have only 1, 1 because 1, 0, 1, 0. So here you have 2 zeros here. But you should not start with 0. So you need to bring 2. You have to bring 2 bits. So this bit 1 down. When you bring this bit down, you have only 2 bits, not adequate. So I put 0 in the coefficient. In the quotient. And then bring next 0 down, 110. So 1, 101. This step. Then another 1, 101. So finally you get 1, 1. So the answer is D. Students, do you have any doubt? Did you try yourself? If you have not tried yourself, you can give a try. Any doubt for this question? Yes, so straightforward, good. Question number 7, with sentinel-based framing, at most how many additional bits need to be transmitted for a 20,000 bit frame? For question number 7, okay, there's a chat from Benita. Okay, I'll come to it later. Okay, so at most how many extra bits need to be transmitted when 20,000 bit frame is sent? So you note that for every 5 consecutive ones, the sender adapter will add 1 extra bit. That is the additional bits or stuffed bit. So in the extreme case, or in the worst case, if all 20,000 bits are ones, 1, 1, 1, 1, 1, 1, then for every 1, we have to insert an extra 0, right? Every 5 ones, for every 5 ones, there is an extra 0. So 20,000 divided by 5 will be 4,000 extra zeros will be there. Okay. Now,
Prof,
yes.
for this, so you are using bit stuffing, but why not use byte stuffing, where you have an extra byte for every escape character?
Okay. We don't use byte stuffing here because the question here is how many extra bits. Okay, if I ask extra bytes, then you can infer that it's a byte-oriented protocol. Okay. PPP is a byte-oriented protocol. It carries bytes, not bits. Okay. So though it's not explicitly mentioned, right? When I talk about bits, you can assume that it's bit stuffing, not byte stuffing. Okay, so that refers to STLC kind of bit stuffing. Is that clear?
Then Prof, I just want to check. So is HDLC the more commonly used one in the real world?
TLC or its variant. Okay, so there are different variants. Okay, PPPP is also used. I think I mentioned, okay, PPP is also used, HTLC also used, and a variant, the different variants of HTLC also used. Okay, not in the local area context within our organization and all, but it's mostly to connect the routers by the link. Okay, it's is it okay?
Yeah, thank you so much.
Yeah. So because I talk about extra bits, so you can infer that it's bit stuffing. So it's not byte stuffing. Number 8, two hosts A, B attempt to transmit on an Ethernet. It's also similar question we discussed in the tutorial, but it's slightly different numbers here. Each host has a steady queue of frames ready to send. At a given instant of time, the two hosts attempt to send the frames simultaneously and collision occurs. So that means the hosts enter into a back-off race. So suppose the collision count or the collision is the second and fourth collision experienced by host A and B. Okay, so note that the collision count for the host may be same or different because it is local. Okay, A doesn't know the collision count of B. So as far as A is concerned, it is the second collision count. That means the previous frame was also collided. Now also there is a collision. So it's second. Similarly for B, it is fourth collision. So how the exponential backup works? A will choose a random number from 0 to the interval 0 to 3. B chooses a random number in the interval 0 to 15. Okay. Now we need to calculate the chance or probability that host B wins the race. Host B will win the race these three cases. B may get 0. When B gets 0, A gets a number greater than 0. Okay, then B will win. So there are three possible cases. A is 1, 2, 3. Similarly, if B gets 1, A gets a value greater than 1. There are two possibilities, number 2 and number 3. In that case, also B wins. When B gets 2 and A gets greater than 2, that is A gets 3, there's only one possibility. Okay, so then in that case also B wins. But for all other cases, let's say B gets 3, 4, 5, 6. In all the cases, okay, B cannot win. B cannot win. Okay. So total 3 plus 2 plus 1, 6. There are 6 possible combinations or possibilities out of total 64. How we got this 64? Because A has 4 possibilities 0 to 3, B has 16 possibilities 0 to 15. So 4 multiplied by 16 is 64. So 6 by 64. This one. So there's a question by Brian, how we get 0 to 3 and 0 to 15. Okay, so this, according to this method, depends on which collision it is. If it is the second collision, this is 0 to 2 square minus 1. It's exponential backoff. So 2 square minus 1 is 3, 0 to 3. If it is the fourth collision for B, fourth collision is 2 raised to the power 4 minus 1, 15. That's why B chooses a random number from 0 to 15. That's how we get it. Is that clear? It depends on the collision count. Okay, good. So question number 9. Another interesting question. Consider a sliding window based flow control protocol that uses 3-bit sequence number and a window size of 7. So window size is given 7. At a given instant of time, so sender side, the window is 2. So the window size is 2. And the window contains frames 3 and 4. current window shows the sequence number 3 and 4. Now the sender receives RR2 and updates its window. What does the new window contain? How it will be updated? That's what the question is. Okay. Now, current window shows 3 and 4. That means window size is 2. That means what? There are 5 outstanding frames. Why there are 5 outstanding frames? The window size is 7. Total window size is, maximum window size is 7. Current window size is 2. So the outstanding frames, number of outstanding frames is 5. There are 5 outstanding frames. They are nothing but 67012. How do I get 67012? Look at the 3, 4. Before 3, the earlier frames. Before 3, we have 2. Because prior to 3, it should have transmitted 2, then 1, 0, 7, 6. So the previous 5 frames is nothing but 67012. So these are the frames, outstanding frames. So if you look at the lecture notes, this will be something like this. This is 3, this is 4. Okay, the window has 3 and 4. Right? And this is the vertical bar. You have frames 6, 7, 0, 1, 2 here as per the lecture notes. So these are the frames which are outstanding. That means they were sent, acknowledgement not yet received. Now, the question says it receives RR2. RR2 means what? The receiver is ready to receive frame number 2 onwards. That means it acknowledges all the frames prior to 2. That means it acknowledges 6701. That's what it means. The receiver has received 6701. It has not received 2. It is ready to receive 2. So because it acknowledges 4 frames 6701, the window will expand by 4. Current window is 3, 4. When it expands by 4, the new window will be this 6, 3, 4, then 5, 6, 7, 0. It will expand by 4. Any doubt? Students, is that clear? Why expand by 4, not 5? Okay. Let me explain it again. Sender receives RR2. RR2 means, as per the definition, the receiver is ready to receive frame with sequence number 2. That means the receiver is acknowledging all the previous frames, frame number 1, 0, etc. So as per the sender, okay, all the previous frame means 1, 0, 6, 7. These are the previous frames. Is that okay? So how many such previous frames are there? Are frames prior to 2? There are 4 frames, 6, 7, 0, 1. So it is expanding by 4. Question number 10. Which of the following statements is true? A DSL-based access network, voice and data transmitted using TDM over the dedicated line from home to central office. No, they'll be using different frequencies, not time. So that's false. Cable modem-based access network is a shared access network because the cable network is basically a broadcast network. So it's a shared access network. This is true. So B is the correct answer. C, drawback of PON-based access network, high BER. This is false because the bit error rate in the passive optical network is very small. It has low BER, not high BER.
So what's the reason for A to be positive? Is it because it's have frequency multiplexing?
Yes. DSL also, yeah, simultaneously it sends on 2 different frequencies. Voice and data transmitted 2 different frequencies. It's like FTM, not TDM.
Okay, thank you.
Okay. Number 11. Which of the following statements is false? Ethernet frame contains an IP packet itself. So A says, what is the meaning of this? A says this is layer 2 header. This is layer 3 header. This is layer 4 header. Ethernet frame contains IP packet means this is a frame and this is the packet. Sorry, this is a packet. So this is the IP packet where L3, layer 3 header appears first. When you add L2 header, Ethernet header, it becomes a frame. So the answer, so the first answer A is correct. It's true, but the question is which is false. Okay. Now, an IP packet contains Ethernet frame. It's not correct. IP packet contains Ethernet segment because if you look at this, this is the IP packet. It starts with L3 and inside IP packet, you have layer 4, that is TCP header and the payload. So that means IP packet carries Ethernet, sorry, TCP segment or UDP segment. Okay. So B is false. C, CRC bits appear at the end of the frame. That is true. So if you look at frame format, CRC will appear at the end. Ethernet switch forwards a frame based on 6-byte destination address. That is correct. So the question is DSL uses FDM. Any other modem uses FDM. Even cable modem also it uses frequency FDM only, right? Video channels and data, internet data all are multiplexed. They are all carried, they are all transmitted on different frequencies at the same time. So cable modem also FDM only. Number 12, a switch has 4 ports labeled 1 through 4. It receives a frame from host A attached to port 1 to host B attached to port 2. When the forwarding table is empty, the switch will forward the frame through. Because the forwarding table is empty, the switch doesn't know where it is, so it has to broadcast. Broadcast in the sense, it will send it to all the ports except the port from which it received. Because it received the frame from port number 1, it will send it to the remaining ports 2, 3, and 4. That message, that's a question. Sorry, Prof. Could you repeat what you said about FDM? The question was FDM, okay, which modem uses, right? Whether, because we were talking about ADSL modem also uses FDM because voice and data are sent on different frequencies at the same time on the channel. If you look at cable modem also uses FDM because by nature, when you say cable TV network or cable, different cable channels, that's a video channels, are broadcast on different frequencies. Okay, it itself is FDM, and some video channels are used for data transmission. So as a whole, even cable modem uses FDM. That's what I said. ADSL modem also uses FDM. Cable modem also uses FDM. That is transmission from cable modem to the internet. Is that clear? Benita, I believe should be clear to you now. Question number 13. Which of the following is true for an Ethernet switch-based extended LAN? Okay. Backward learning, yes, that is correct because Ethernet switch-based LAN uses backward learning to learn where the host is. Shortest path spanning tree, yes, it uses shortest path spanning tree for frame forwarding. Then C, possibility of bandwidth waste, as some ports may not be used for frame forwarding. That's also true because when you form a tree, some ports may not be active. That means we are not using those ports for frame sending and receiving. So the answer would be D, all of the above. All the above, that is A, B, C, all are true. Question number 14. To detect a collision in a broadcast Ethernet LAN, the frame transmission time must be at least round trip time. I think this I explained at length in the lecture. You can go through the lecture notes again. Yes, the frame transmission should be minimum 2 times the round trip time. That is true. And question number 15, maximum number of bits that can be transmitted in 1 second. Maximum number of bits that can be transmitted in 1 second means the link capacity or channel capacity. Channel capacity is the maximum data rate. That's what is asked. If 8 megahertz TV channels, so our TV channels, okay, the TV channel bandwidth is 8 megahertz. That means one video content that uses up, one channel uses up 8 megahertz. So that you can see, if you want to look at, if you want to manually tune or anything, you can see the frequencies of the channels. Yeah? You will see the difference of 8 megahertz. So in this case, what is the capacity? So what is the, so this question is to show the relationship between the data rate and the bandwidth. Bandwidth here is 8 megahertz. This is the true definition of bandwidth measured in hertz. Okay? So we use this equation, this theorem, which we already explained, studied in the class. C, the capacity, that is bits per second, equal to B, bandwidth, multiplied by log 1 plus signal to noise ratio. The signal to noise ratio quality is given as 60 dB. Okay. So 60, that means you look at the second line, 60 equal to 10 log, because it's expressed in dB, decibel. So you need to know the notation, 60 equal to 10 log S over N. Okay. So 60 is, sorry, maybe I can write it here. 60 is 10 log, 10 log. Okay, this is base 10. So 0, 0 can cancel 6. So obviously, S over N is 10 power 6. 10 power 6 is approximately 2 raised to the power 20. Yes, because it asks approximately. If you have calculator, you can find the actual value also, should be okay. So approximately 2 raised to the power 20. Why I'm using 2 raised to the power 20 here is that in the capacity formula, B log 1 plus S over N, the base for the log is 2. So you can see C equal to 8, B is 8 megahertz times log 1 plus 2 power 20. 1 plus 2 power 20 is 2 power 20 approximately. Okay? So log base 2 power 20 is 20. So 8 into 20 is 160 Mbps approximately. If you use calculator, you may get maybe slightly different number, but which is close to 160. Maybe you may get a slightly smaller one, 158, 156 or something like this. You can use calculator. Yes, the quiz, the test, you can bring your calculator. That's okay. So this is the end of the discussion of this question paper. I'm done. Okay, if you have any questions on this sample paper or any lecture topic, you can ask now. For question number 9, why is frame 2 is not in the window if it is not acknowledged yet? For question number 9, I think the meaning of window is this. When you say window has 3, 4, that means in future, sender is permitted to send 2 more frames whose sequence numbers are 3 and 4. So window does not show the frames which were sent out. No, the window shows the sequence number of the frames which it can probably send in future. So 2, that means 2 is an outstanding frame. It has been already sent out. It's a chat question from Pranav. Large formula like link utilization for go back N, yes, that I'll provide. Okay, if there's any question on go back N ARQ, I'll provide the formula. Similarly, if there are any numbers to be memorized, like T1 bandwidth, T3 bandwidth, T1 link, T3 link, okay, because there are some tables I've given. Okay, the data rate of, let's say, OC3 signal, T1 link rate, etc. Those numbers I'll provide if there's a need. There's a question from Benita. For fixed TDM, can we always assume that there is no congestion because each input is assigned fixed time slot? Yes, in fixed TDM, there is no congestion because all the bits and bytes, whatever it is received within a certain time period, are guaranteed to leave on the output link. So there's no question of excess bits queuing up and congestion dropping and all. No, fixed TDM, there's no congestion. This is a question, paper written or canvas? Which paper you are talking about? Quiz question, is it? The question, the quiz is going to be in person, right? LT11. So I already posted it. You should write it on the question paper. This is the sample question paper, right? There will be answer table like this. Just you need to enter A, B, C, D something there. So there's a question from Benita. May I ask if the frames entering and leaving a switch is equal? Does the switch still need to retain a buffer if it needs to receive the entire frame before it can start propagating? Yeah, that buffer is always required. When the frame is received, it should be put in a buffer. Okay, so that we cannot avoid. That should be there. Even in fixed TDM, when the bytes are received, which bytes are received, some bits or bytes would be there in the buffer. There's a small buffer to hold it. Okay? So that should be there. Are we allowed rough paper for working? Usually I don't allow it because the question paper itself has a lot of spaces. So you can use it because I'm not interested in your working. So you can use the empty space in the question paper. But if you need to use your own paper, first you need to show it to me that it's a blank paper, then you can use it for working. Should be okay. May I ask if I'll scratch the paper before it? What do you mean by scratch the paper? Peng-Fei.
So it's just what you mentioned before, like
yeah.
some
Scribbling.
object.
I think you're basically scribbling, right? You want to write anything, you write. Any working out you do. I'm not going to look into that. Okay, any working, anything you can do. What I will look into is the final answer table. That's all.
Thank you.
There's a question how 15.2 microsecond RTT is Ethernet derived. Okay, so we want a number which is an upper bound in the sense it can never, it's guaranteed that it can never exceed that. So that's an upper bound. Okay, so if you take in Ethernet, the maximum length of the cable allowed as per the standard is 2.5 kilometer. So the bits, okay, you just imagine the worst case delay. One host is attached to one end of the cable, the other host is attached at other end of the cable after 2.5 kilometers. So the bit has to travel 2.5 kilometers. And it has to go through 4 repeaters. So there's some time delay within the repeater. Similarly, round trip means the bit has to come back. It has to travel 2.5 kilometers and it has to go through the 4 repeaters again. There's a delay involved here. All together, it's guaranteed that, okay, maybe safe side, it is 51.2, it's put. Could be practice maybe 40 or 45, anything. So to be on safe side, it is standardized as 51.2. It can never exceed 51.2 microsecond, right? So this is the worst case, upper bound. So that's how it's arrived. Because we also want multiple of 8, like 64 bytes, 32 bytes or something to fix the minimum size. So even though actual number may be 45 or 43, we wanted to keep it as slightly higher number. Any other questions? Students, if you have any other questions, feel free to ask. There's a question for dividing polynomial to see if x plus 1 is a factor. You carry out the division in binary. You divide it by 1, 1. You need to do mod division. You can do binary, so you can do polynomial, but it will be complex because polynomial, as I said, the equivalence is something like plus or minus. So it could be say x square minus x or x square plus x, both are same. So I would suggest you to carry out in modulo or using modulo 2 division. That's the best. Okay. So if there are no other doubts, can we end the session? November 2002, question paper, question 3. What is that question? November 2002. Let me see whether the question is here.
It's the question on the PCs and what adapter I should choose for it. I can share my screen. Is that your help?
Okay. Yeah. Okay. Please.
Give me a second.
We will try to release one more past year paper, recent papers before your final exam. Okay, I will discuss with Prof. Mehul Mottani, the other lecturer. Okay, because these questions were quite long time back. Some questions are out of scope also. Yeah. Are you able to share?
Yeah, sorry, give me 1 second. Yep, this question.
Question number 3.
Mm.
I think this you asked in the email also, if I remember correctly, right?
I didn't understand your response because it said that
Okay. Okay, you see how long it will take to do the backup. So it says there are 12 PCs, one server connected to an Ethernet LAN, right? So if nothing is specified, you can assume that it is a broadcast LAN, okay? Right?
yeah,
So you did you calculate how much time it takes?
because if it's 12 times 1,000,
So for one PC, how long it takes to backup?
1,000 divided by is
Now,
basically 1,000 seconds.
1000 MB, right?
Yeah,
M
so
means
1,000
2 raised to the power 20, right? 1024, 1024. Then byte is 8. And the data rate is 10 Mbps, correct? How much time you get?
Or 1,000 times 10 to the power of 6 times 8 divided by 1 million.
1000 times million is 2 raised to the power 20, okay? Byte is 8. So that is the size, total size, right? Divided by 10. That gives you how much time it needs for one backup, one PC backup, correct?
Oh, okay.
So you have to multiply it by 12. 12 pieces need to, because it's a broadcast, they cannot do at the same time, right?
Yeah.
So if the total time is less than 24 hours, obviously you can go for cheaper option, right? For 1 Mbps, 10 Mbps. Okay, with 1 Mbps, if you cannot finish it in 24 hours, even if the adapter is cheaper, we cannot go for that, right? Because it has to be done every day. You need to check whether you should be able to do it within a day. If I am not wrong, if I remember correctly, when you use 1 Mbps adapter, you may need more than 24 hours.
Oh, yeah, I need 28 hours.
Or 28 hours. So that's not an option. Rule out. Okay. Is that clear?
Oh, yeah. Sorry, I think I got confused with this data part.
Okay. Yeah. So the questions are not tough. They are easy. The exam paper also easy. Okay. Just practice and try to understand the notes and the concept. It should be easier. Okay. For the quiz also, some maybe calculation based, some okay, true or false. There could be some questions match the following kind of things also. In the sample, it is not there, but you may be asked to choose the correctly matched pair, okay, which is correctly matched, okay, which is false, which is true, okay. So there are multiple type of questions in the MCQ type. But as I said, MCQ has pros and cons, okay. I think I explained in the class. Sometimes you guess, you get a mark. This is a reward. I mean, you get, your guess may be correct. You may not be knowing exactly the answer, but somehow you got the correct answer. Right? Sometimes you work out, but you end up with the wrong answer. You may lose. But as a whole, okay, when I conduct MCQ or the written exam, the average mark of the class, more or less, usually it will be between 10 and 11, sometimes close to 11 out of 15. sometimes close to 10. So for this batch, I expect more. Let me see what is the average this time. So next, oh, you want the answer for this question?
Yeah, as in because for this question, I realized that the only address that you need is B. But when the question is phrased this way, when they say that two holes are like, is it as long as it contains B in the answer, I can pick it? Or
Let me read the question. Okay, 1 minute. So many yes questions we said. Okay, switch has 4 ports, 1 to 4. A and B are on the same line. Okay, port 1, C and D are connected to port 3 and port 4. First A sends a frame whose destination is host B. Upon receiving this frame, the switch does not forward it. So it knows, okay, the B's destination,
yeah,
correct?
yeah. As in, I'm just asking like I picked option A, which is B and D, because there's the only option with B inside. But in this case, it does not need to know where D is. Right?
No, but the question says the switch had forwarding capabilities for 2 hosts, right?
Okay.
Am I correct? So that
Yeah.
means, yeah. So you should choose the one where B is there, right?
Okay.
That's correct.
Okay. Thank you, Prof.
Okay, good. So other questions? Any other questions? Well, yeah, today part 2 started, right?
Yeah, Prof.
Yeah, okay. So if there are no other questions, can we end the session? Okay, students, I'm going to end the session. So if you have any other questions, you can send me an email. So I will try to answer as quickly as possible. So send us maybe a screenshot of your question. Be easier for me to respond quickly. So I meet you again on Wednesday, 1 p.m. LT11. Please check before the where is that LT11. You may not be knowing it, okay? Because I want a bigger lecture theater so that some sufficient space is left between the students. It's an exam, it's a test, okay? So we are meeting at LT11 on Wednesday, 1 p.m. See you then. Wish you all the best.
Thank you, Prof.
Yeah, there's a chat. LT11 is FASS. I think so. I will not be there. For me also, it is new. I have to search for it. But what I understand is, yes, somewhere next to library, I think LT11. Please check yourself. Be ready to locate it. See you then. All the best.